Okay, in this video we're going to consider some additional situations where you may have observational multiple sample study designs or experimental parallel sample study designs, but that you have more than two groups in these studies. So you have more than two independent samples in your study design. So let's talk about what that might look like. So in this type of study design you have more than two samples of individuals. And again, you've collected data on some continuous variable from these individuals, and you're interested in how the many sets of independent data differ from one another. So imagine, for example, you have three groups, and you want to compare the strength values between these three different groups. So you may compare these three groups, or you may have an experimental design where you again start with a single group of individuals that you randomize into three separate samples. You maybe apply three different interventions to these groups, and then you want to compare the effects of these different interventions. Let's remind ourselves quickly of our two independent samples design. And in this we had the similar regression general linear model that was introduced in the very first lecture of this series, which is quite simple to do when we just have two independent groups. But when we have more than two, let's say for example 4, it can start to get a little bit more complicated. But there is still a very similar underlying principle that applies to this kind of data. All we have to do is again apply our dummy coding scheme. Now, one of the things you'll notice is that we now have beta 1, x1, beta 2, x2, beta 3, x3. Let's have a little look at the different coding schemes that we'll use that will allow us to fit a general linear model to this kind of data. So we can code x1, x2 and x3 for example. And all this is a way of coding it up so that the model knows which group is which. So for example, the first sample we would code as being 0, 0 and 0. And all that says is that all of these beta 1, beta 2 and beta 3 all become 0 because they're multiplied by 0, which means that the beta 0 here, our intercept in our model, is essentially what we're saying sample 1 is. We code sample 2 as saying that x1 is equal to 1, but the remaining x's are equal to 0. That tells us that that is group 2. We shift it along, x2 becomes 1 for group 3, and x3 becomes 1 for group 4. This is how it looks when we then plug that in and think about how that coding refers to our general linear model. So, as I said, sample 1 essentially becomes our slope. So this becomes the mean for group 1. If all the other variables, parameters in the model are being times by 0, then it means that all we're left with is the mean for our first group. Then what we have are three different slope values, which all give us the differences between sample 1 and the various groups. So for example, beta 1 would tell us the difference between group 1 and group 2. Beta 2 would give us the difference between group 1 and group 3. And beta 3 would give us the difference between group 1 and group 4. Now, we can obviously shift around our coding scheme so that we can use different groups as reference values. For example, if we had a control group, we might want to set our coding scheme so that we can compare each of our other groups to that control group. You can set it up however you like, and there are in fact other ways of coding this up to get different kinds of comparisons from your regression model. We can also calculate again from these the different means for each of the different groups. But normally what we would use in this kind of analysis is what is called a one-way analysis of variance. But essentially this is all that it is doing. We fit our model to compare the differences between the groups and some reference groups. Again, we can use a non-parametric version of this where we rank transform our y values, fit the same model, and this becomes something known as the Kruskal-Wallis test. Again, there will be some videos to show you how to do these in JASP and to show you the equivalence between these kinds of models.